This section, we're going to talk about transformations. So we're going to talk about transformation of functions on a graph. The objectives here is to determine the transformation under translations, reflections, stretching, shrinkings. Let's go to it. This one here, if you wanted to pause this and screenshot this, I would encourage you to. These are going to be really helpful tools because whenever you got to make a transformation, you want to be able to take an original and then apply the changes to it. And I'm going to go over that with you here in just a minute. And let's look at this. The identity function, this y equals x. If you notice, y and x both have a degree of 1, so it's a linear function. And if you notice, it's a straight line, and that's what a linear function is. It doesn't necessarily mean it gives you this particular point because we haven't added or subtracted anything to the x value. So the squaring of the functions, if you notice, y equals x squared, so we got a parabola. If my x had a negative in front of it, if it would have been negative x squared, it would have opened downward. This next one is square root function of y equals x, or square root of x, and you noticed it opens this way. If it had a negative in front of the square root, it would have opened that way. This next one's a cubing function. I got y equals x cubed, and if you notice, I got this function here. However, it would flip this other way if it had a negative in front of the x cubed. I got a cube root. So y equals cube root of x. So this is what I got going on. If it would have been a negative cube root, it would have looked like that. The reciprocal, so I got y equals 1 over x. So whenever you look at the denominator here, the denominator is going to have restrictions, right? So we can't have 0 there. So when x equals 0, this is it's not a real function. So that's why this function has to split apart at where it causes it to be undefined. And that's what we got going on around it. All right, the absolute value. So I got y equal to the absolute value of x. We get this right here. If there was a negative sign in front of the absolute value, it would have opened downwards. Okay, transformations of functions. These functions can be considered building blocks for many other functions. We can create graphs on new functions by shifting them horizontally or vertically, stretching or shrinking, reflecting across the axis. So let's talk about an examples of this. Let me get my screen to scroll. All right, so let's look for the vertical translation. So here it is. If I have f of x is equal to something, we can also say y equals f of x. And let's just look at it. I have this function, and then this is like saying I have y equals x to the first power. I can graph it. That's what I would want to graph first, and then apply the changes. In this case here, if I had a plus b, I would lift it. If I had a minus b, I would lower it by whatever number the b is. So over here, if you notice, they have y equals 1/5 x to the 4th plus 5. They said, okay, well, let's plot the y equals 1/5 x to the 4th. After we plot it, then let's apply the positive 5. That means we're going to take this original function and shift it up 5. So I would have a separate sheet of paper for your notes. That way you can write these little formulas to, like, vertical shifting, horizontal shifting, and you can keep it separated from your actual written work. It might help you when you do your homework and study. Horizontal transition says that, so I have this y equals x. And if my x inside here becomes minus d or plus d, then I'm going to have shifting to the right or shifting to the left. That's my horizontal shift. All right, so we have this notation here of y equals f of x minus d. If it is minus D, we're going to shift it to the right, the D in the unit. So however many D's it is. If it is a positive D, we're going to shift it to the left. So if you notice here, this example had a +7. So we had to grab this and move it to the left 7 times. Okay. This one here says that the reflections, let's talk about it for just a moment. It says that a reflection about, okay, let me just read it, okay? So the graph of f equals negative f of x is a reflection of the graph because we're going to flip it. So when I was talking about how those ones, if it had a negative in front of it, it would flip it. So this is what it's telling you. So it would cross the x-axis, right? If your function looks like this and then you plot the negative and it flips it, it was a reflection about the x-axis. So if the graph of, so that was this one. Now, if you was to apply it to the inside here, then it would be a reflection about the y-axis, right? And then the last part says, if a point is on the graph of y equals f of x, then x comma, whoops, sorry guys, I put a negative there. Let me erase that. Okay, so then we have this ordered pair here of positive x comma negative x. And then we can flip it and we have a negative x comma y. If we have this, then we have a reflection, right? About the origin. Okay. So now let's do our examples here. It says graph each of the following before doing so, how each graph can be obtained from the graph. So, you'd graph it and then we're going to see how it's obtained from the graph. And we're giving here f of x is equal to x cubed minus 4x squared. So we're going to rename it. We're going to call it G because we're going to make changes. I'm going to apply the negative to the x. So I want to put the negative on the x. So now I got negative x cubed minus 4 negative x squared. And I should have put the parentheses on that. There we go. Clean that up a little better. So if I take this negative value to the odd power, it gives me negative. If I take this negative here to the even power, it just gives me even. Okay, so now we want to compare those. So this is my G of X, right? We want to compare if this gives me back my original. And if you notice here, it's not giving me my original. So therefore, I would state this is this graph of G is a reflection of the graph of F across y-axis. Okay. On B here, we have 4x squared minus x cubed. So it's just written in a different format and moved the negative sign back. How did we know to do that? Because they applied it to this. So that means I would have had negative x cubed. Well, let's do it this way. It just skips some steps, okay? So I'm going to apply this negative here. So now this is where we get the negative x cubed plus 4x, which can be written in this format here. Now that we've done that and solved for B, we can determine what it's reflected about and compare it. And then this one was called H, right? So this graph here is a reflection of the graph of across the x-axis. Okay, so this one's reflecting about y-axis, and this is about the x-axis. All right, so this would have been f of x is equal to negative f of x. This one would have been f of x equal to f of negative x. Okay. Make sure you didn't skip. Okay, this next slide is just showing you what this function looks like. If I have x is positive here and negative here, and y's are both positives. In this case here, the order pair they gave us was the only thing different was the signs on the x value, and then we get this function that looks like this. This will get easier after you do them multiple times. That's why I say put your formulas and your instructions on a separate sheet of paper. It may be helpful. Make sure I didn't skip a module. Let's see, did I skip one? My apologies, guys. I'm going to go backwards. It feels like I skipped one. And with this jumping around like that, it makes me wonder, did it just delete a slide or something when I saved it? Okay. All right, so this next one is just telling us about, or we're gonna solve this next one, but I wanted to talk about the shrinking, the vertical shrinking, and let's see, is that what the next one, the vertical shrinking? I feel like it skipped it. All right. Oh no, there it is. Okay, good deal. All right, so on this next one here, graph each of the following before doing so, describe how they change. So this slide appeared twice. We just solved this one. If we plugged in the negative value for the x, right? We were looking for the y-axis. If we plugged it in for outside of the function, which is our y value, then we're looking for the x. So yes, it did show it twice. There it is again. So now this is the next slide we need to get to. I kind of knew it was there, just my apologies. All right. So the vertical stretching and shrinking, the graph of y equals, and if you notice here, you see that it has an A here. So this A is going to tell me if it stretches or shrinks, or if it shrinks. All right, this says here a stretching of the vertical, stretching vertically. So if the graph stretches vertically, that means the absolute value of A is greater than 1. Okay. The sign on A just tells me if it opens upwards or downwards, to the right, to the left, if you flip it, right? So that's why they're showing the absolute value, because the negative and positive applies to it differently. Where A itself says if it's greater than 1, then we got a stretching. If A falls between 0 and 1, then we got a shrinking going on. Okay. If A is less than 0, then we have a reflected across the x-axis. Y coordinates of the graph of y equals a f of x can be obtained by multiplying the y coordinates of at y equals f of x, okay, by a. Okay, so now let's look at this one right quick. So this example 2 here, we are giving this, we're giving this function y equals 1/10 times x cubed minus x. So if we just took the y equals x cubed minus x and plotted it, that's this black one here, and then we looked at the 1/10. 1/10. If you determine what 1/10 is, you can divide it out and you can see that it gives us 0.1. So we'd agree it fell between 0 and 1. So since it falls between 0 and 1, the rules told us up here, right? It says we have a shrinking going on. So if you see it, it looks like it kind of stretched out. Our curves are not as curvy. We got a shrinking of the curves. Okay. However, on this next one, it said, okay, we have y equals 2 times x cubed minus x. let's take out the y equals, take the a out, because a in this case is 2. And look at the x cubed minus x. And if I plot it, that's this black one. And if you look at A has a 2. 2 is greater than 1, right? So A is greater than 1. So we have a stretching going on, and look what happens. Our curves become more prominent. They become bigger peaks, right? So we got the stretching going on. Now, again, if A was negative, if this was a -2, it just means that we would flip this and it would be a reflection about the x-axis, and, you know, it would just flip it. That's why they said absolute value of A. All right. And here's you another example. Look, this is where I was talking about. So we got y is equal to -2x minus or times x cubed minus x. So my A is absolute value of A is 2. I have this negative going on. So that means I'm going to flip my function on the graph, and it became a reflection about the x. I plotted the y equals x cubed minus x, which is this black one. The 2 gave me that higher peaks or valleys, higher peaks and valleys on the function that we're applying it to. And then it flipped it because of the negative sign. Horizontal stretching and shrinking. So let's talk about it stretching horizontally. So what we got here is a graph of y equals, and then we have f c of x. Okay, so we was talking about where a f of x. Now we're talking about cx, right? So now let's look at it. We can obtain this information. This is going to be stretching vertically, or excuse me, we just talked about vertically. This is going to be stretching horizontally if the absolute value of C is greater than 1. This is going to shrink horizontally if C falls between 0 and 1. Okay. And this will be a reflection about the y-axis. Okay. Let's look at it. So if you notice here, we have this y equals x cubed minus x, and it's in black right here. And then we said, oh, well, let's let C be 2. So we agree that C is greater than 1. So remember, we go back up, let's look at it. It said, if C is greater than 1, then we got a stretching horizontally. So look at our they came in together. You know, the lines are coming in closer together of this function because the peaks and valleys become more prominent, more dominant, right? Like more of a peak and valley. If it was a shrinking, then that wouldn't be that much curve to it. So here you go. Here's one I was talking about. So here's our shrinking going on because our C is a half, which falls between 0 and 1. So we have this more, see, it's not as high of a peak, right? So thank you.